I'm going to talk about some of the common challenges we have growing cotton. Some of these challenges they can be overcome by the use of biology and nutrition. So, poor seedling vigor. High dollar seed, we get it. 60% germination at best at times. Just a little bit of a crust, doesn't want to push out of the ground. So this is one of the issues that we have to deal with consistently in growing cotton. After the cotton's up, of course, we have pests that we deal with. Thrip being the number one post-emergence pest that we deal with. Thing about thrip, they're hard to scout for. Of course, we know that. So that's why most people do like a seed treatment or post-emergence application, just broad acre, just do it across everything just to ensure. Just because you usually don't see the damage until it's already happening to the crop. Next challenge, excessive growth. If a cotton plant is eye level, especially to me, it's way too tall. So that's a challenge that we have to deal with, is getting excessive growth in our cotton. Some of the late season pests that we have to deal with, another issue, especially down in the Delta area where they have a lot of stink bugs, but we have everything from aphids, bollworms, flea hoppers, stink bugs, any of the plant bugs. There's a whole list of other pests that we have to deal with in cotton, but those are some of the major ones. And then late season square retention and boll retention. We have all this squares on the cotton and stuff like that, and in late season they all drop off. And why does a cotton plant want to put on all that fruit just to drop it off? So something we'll speak of. David?
You're all surprised by those challenges, right? You didn't know you have those problems, huh? I think you probably did. What I'm going to talk about is how we look at those things, and what we are really looking at is why are those problems? Why do we see those things? Instead of just saying, here's a bug, we must kill the bug, I want to know, why is the bug there? If we have problem with seedling vigor, I want to understand why. Does that seed not have energy? What's the reason? If we have issues with shed and boll drop, what's the reason? Can we learn why? And so we'll look at some of the reasons that we have observed, and I'm sure there's more. Well, I know there's more than we can cover here. So I'm going to go through this quite quickly, and I want to say that it's oversimplified. If you're here and you're a scientist and you understand plant physiology, then this is oversimplified, so we, as farmers, boots on the ground, are able to understand and comprehend it and wrap our mind around the complexity of what's really happening within the plant, within the soil. We're going to look at photosynthesis, protein synthesis versus proteolysis, symbiotic relationships and the cascading sequences, and then carbon distribution management, or the sugar sinks. First of all, we're going to talk about photosynthesis, which is the process by which green plants change the sunlight energy and carbon dioxide into usable chemical energy that then the plant is able to utilize to continue building and growing. This energy, this chemical energy, is called glucose, so a very simple sugar called glucose. Let's look at how it happens. And as we do this, I want you all to be thinking about, where's the limiting factor on my operation? Whether you're growing pecans, whether you're growing cotton or onions or peppers, what is keeping this from happening on my operation? So, sunlight hits the leaf, and let's just look at the leaf. If we kind of take that leaf apart, we're going to see within the cellular structure the chloroplast. And within the chloroplast is the chlorophyll. The leaf will absorb carbon dioxide through the stomata, and into this chlorophyll molecule we get carbon dioxide, and through the roots we get water. So the sunlight now hits the leaf, the carbon dioxide and the water are reacted. There's a reaction that happens from the photonic energy, and the plant releases oxygen, and sugar or glucose is created from that reaction. Now, in order to build the chlorophyll molecule, we're going to need at least, at the very minimum, 3 minerals. We need magnesium, we need nitrogen, we need iron. How many of these are on your regular fertilizer tag? Do you have enough magnesium in your soil? Do your plants have enough magnesium? Because if you don't have magnesium, that's the center of the chlorophyll molecule. So not enough magnesium, less chlorophyll, less sugars produced. And then nitrogen and iron puts that together. All right, so now we think about the carbon dioxide that the leaf is absorbing to be reacted. Well, we need to think about, do we have all the nutrients that the plant have, the minerals that it needs for the stomata regulation? How many times when you walk through your plants, you're looking at, wonder if the stomata are working? Yeah, we kind of look at our leaves and we say, oh, nice crop, great crop. Or maybe you're going past 50 miles an hour and you say, nice cotton, or ooh, bad cotton. But you never think about the stomata, the little openings that open and close to allow carbon dioxide to come in. So just that simple little thing is enough to reduce your sugar production and allow your plant to be less productive than it could be and more susceptible to insects and diseases. So think about the stomata regulation in your plants, in your crops. Are the stomata opening? Are the stomata closing? When it gets really hot, you want those stomata to close. You don't want a lot of extra water to be evaporating. So opening and closing of stomata is very important for plant health. There's many enzymatic reactions that happen with that. We know that potassium and silica are 2 very key ones. Again, like I said, this is simplified. There's more that happens than we can describe in a short period of time. And there's probably a lot that we don't yet understand. Okay, so we get carbon dioxide from the atmosphere, right? We were just talking about carbon credits. And we have all this talk about how much carbon dioxide we have in the atmosphere. So we can get carbon dioxide uptake from the atmosphere. But my belief is that the most of it comes from the soil. Now think about your soil. Do you have enough carbon in your soil that the plant is able to get enough carbon dioxide to get you the maximum yield? What if you don't have enough organic matter? What is your organic matter level? What are other things that might keep that carbon dioxide from being released from the soil and being captured by the plant? Something very important about organic matter and carbon. It's not about the levels that you have in the soil. Like if I have 2%, 3%, 5% in my soil, then all is good. It's not so much about that as how well you are cycling the carbon. Is it being released from the soil and is it being captured by the plant? And I will say that most of agriculture's challenges today come from that cycle being broken, because when there's excessive tillage and there's no plants to absorb the carbon dioxide, away it goes. Because there's no plants there to capture it. That's why cover crops are so important. It's because as the carbon oxidizes, or as biology works on the organic matter, and it's released and there's no plant to capture it and put it back down, it goes into the atmosphere. We must cycle the carbon. What else is important when we think about cycling carbon? We need bacteria. We need fungi. A soil that's sterile, a soil that doesn't have life, isn't going to release carbon dioxide. Think about a forest. Think about a forest. When does the carbon dioxide release happen? When the biology starts to get very active. And I know a forest is kind of hard out here, right? I'm back from Ohio where we have big woods and there's leaves and there's lots of carbon. That carbon cycle doesn't really happen until there's a lot of leaves. And then the fungi and the bacteria get the food, the sugars that go down through the roots, feed the biology, and then carbon dioxide is released, and it goes up, and the plant grabs it and puts it back down. Tillage. When we expose the soil to oxygen, to the air, then it will oxidize the carbon, and you also get carbon dioxide released into the atmosphere, and there's no plants or not enough plants. If you just have a row of cotton and you're cultivating the whole acre and you just have these little bit of plants, you're not capturing all of the carbon dioxide that's being released. Is there something we can do about that? Think about your operation, think about your farm, and think about how it can work on your operation, that whether you're tilling, whether there's microbial activity, whatever it is, that the carbon cycle is completed and that you're putting the carbon back down in the form of root exudates. The next thing we must think about is water. If we don't have enough water, then we don't have H2O for that photonic energy to react with CO2 or carbon dioxide. So, how's the water on your farm? How do you maximize yield? Do you stress your plants and make sure they don't have enough water so they don't, like Kip said, grow too tall? One of the ways is reduce the water. Yes. But that means the plant is not photosynthesizing at its maximum capacity, which means you have less sugars, which means you have limited your yield potential. You have limited your quality potential because you are not giving the plant the water that it needs to photosynthesize and to put carbon back into the soil. So managing water, not too much water, not too little water. What about water uptake? There's a problem, not just with water uptake, but with water percolation, with water being absorbed into the soil, and organic matter is number one. When there's a crust on the soil and you get a rain, there it goes. All of the water that you wanted for your cover crop is in the ditch. But if we have soil structure, if we have lots of organic matter, we're able to hold that water, and not only does the water go down and stay in place, but the water can move back up. Called percolation, going down, coming back up. So, what would limit water on your operation as you think about your pecan trees, as you think about your pistachios, as you think about your cotton, as you think about your onions, your peppers, whatever crop you're growing? Do you have a compaction layer? Is there something that keeps the water from percolating down and coming back up? Is there something that would hinder the plants from having a good level of water? Fungi is very important for water uptake by the plant and root growth. So the fungi will be an extension of the root growth. If you have fungi that have a symbiotic relationship with the roots, it's same as growing a bigger root, and the fungi is able to extract water from the soil colloid that the root can't. So, when you have a good fungal to plant symbiotic relationship, then you're going to be able to have better water uptake. But what about water utilization? What if your plant takes up water but doesn't have manganese, which is one of the key enzyme cofactors that is needed for that water molecule to be split, called water hydrolysis? Remember, we're taking CO2 and H2O, 6 atoms of carbon dioxide and 6 atoms of hydrogen, and that's being reacted by the photonic energy in the chloroplast, and we're ending up with C6H12O6, and 6 oxygen molecules are released. But if we don't have manganese, this water molecule can't be reacted. It can't be split. The hydrogen and the oxygen can't be separated. So if you have limited manganese, maybe you have good organic matter, maybe you have good fungi, maybe you have good root growth, but you don't have manganese and your plant takes up water, but your photosynthetic capacity is limited by the plant's ability to split that hydrogen and water molecule, or I'm sorry, the hydrogen and the oxygen in that water molecule. And so our production of sugars is going to be limited. So, photosynthesis, sun shines. How many of you can make the sun shine or not? Can you make the sun shine? No. If it shines, it shines. If it doesn't shine, we wish it would. Unless we need rain. Carbon dioxide. There's lots of things we can do about carbon dioxide. Think about it on your operation. Think about how you can increase the carbon dioxide. And there's something that happens. I don't know if you've ever cultivated corn, or maybe it happens with cotton too. You do a cultivation and it looks like the crop's a lot greener right after the cultivation. What happened? There's a couple things that could happen. You might be oxidizing, some nitrogen might be being released, but primarily it's because there's more carbon dioxide being released and the plant is photosynthesizing more efficiently, and you get this flush of growth. You have more sugar production. And then there's 5 key elements that we need. We need magnesium, nitrogen, and iron for the chlorophyll molecule. We need phosphorus for the adenosine triphosphate, which is the energy molecule that kind of makes the whole machine work. And we need manganese to split the water molecule. So, photosynthesis creates glucose and releases oxygen. And aren't we glad? Take a deep breath. We're glad for all the oxygen we can get. And we're glad for all the glucose that we can get. You all understand that? You know exactly how that works. I mean, what's the plant now do with glucose? Okay, well, let's talk about protein synthesis. Anybody want to explain exactly what's happening here? We could go into and bore you with all the different, how the protein has the mRNA, the messenger, and how it takes amino acids and then builds it into proteins. That's kind of what we're going to be talking about here, is protein synthesis. But I'm going to use an example that hopefully, and for me, help me to understand a bit better what we mean when we say protein synthesis or building proteins. So let's think of a glucose molecule. Instead of the other one that we saw, let's think of it as a chain. How many of you use chains on your farm? Yeah, we know what that is. So let's think of this as having C6H12O6. Okay, so that's a simple glucose molecule. And now by adding a nitrogen or a sulfur or various compounds, this glucose becomes an amino acid. And there's 20, depending what sources you look at, there could be 22 amino acids. And really, it's from this source of energy of glucose, then amino acids, and then those amino acids are put together. So if you think of the different amino acids, like this, well, just a simple example. So if this is an amino acid and this is a different amino acid, these are put together in specific sequences to form a peptide. And every time that we put an amino acid to an amino acid, there's a reaction that happens. Again, kind of like that photosynthetic reaction, binding that chain together. Whenever a reaction happens like that, it's an enzyme is required to make that happen. Otherwise, it takes a long, long time. If you don't have the enzyme, if the plant doesn't have the enzyme, it would take a long time for that reaction to happen and for those amino acids to be bonded together. So let's say you're missing zinc, or you're missing copper, or you're deficient in cobalt, or you don't have enough molybdenum, and it's needed to maybe put together a specific amino acid to an amino acid, then that means that reaction just might not happen. And so now you have a break in the chain, and the plant says, I need a protein to build a new leaf cell. But somewhere in the works, we don't have cobalt, or we don't have molybdenum, and we are not able to have the enzymatic reaction happen fast enough for this plant to happen, and so we have a faulty protein. So let's say now this is a peptide. When amino acids are put together, it's called a polypeptide. So Amino acid to amino acid to amino acid. All these reactions. Every time there's a reaction, you need an enzyme. Every time an enzymatic reaction happens, you need an enzyme cofactor. That's kind of an enzyme cofactor. Another way to think about these enzymes is like an open-end wrench, like a 7/16 wrench. You can use it to tighten a 7/16 nut, but it doesn't work on a 1/2 nut. It doesn't work on a 1/4 nut. Only on 7/16. Same with the enzyme. Enzyme can only put together, say, cysteine and methionine, or a very specific reaction that this specific enzyme can catalyze. But it's not used up in the process, just like your wrench isn't used up whenever you tighten a bolt. You still have the wrench. You can do it again and again and again and again. But if that wrench is in the toolbox and there's no hand to pick it up, there's not something to move that wrench, then it won't tighten the nut. You follow that? So we can have the enzyme, but if we don't have the trace mineral enzyme cofactor, then these reactions also might not happen. Now the next step in protein synthesis is if we take all of these amino acid to amino acid to amino acid, we have a polypeptide. Okay? And now the plant puts together a polypeptide to a polypeptide. And again we have this enzymatic reaction. And then we put it together again, and that continues going on until a protein is formed. Y'all with me? So, what that means is that insects, you remember Kip talking about insects? Insects cannot digest, and digest is the exact opposite of building proteins. It's taking proteins apart. So we eat food. You eat a carrot, your gut will now release enzymes, and that carrot will be broken down into the amino acid form, or even smaller, and put back together in protein for your body to use. Okay? So digestion is the opposite of building proteins. And insects do not have the enzymes in their digestive tract to break this peptide to peptide bond. They can digest amino acids, they can digest free nitrogen, they can digest ammonium and sugars, simple sugars especially, but they cannot digest complex sugars or complete proteins. Do you understand what I just said? Isn't that exciting? So, proteolysis means protein breakdown. And plants are always building proteins or they're breaking proteins. Okay? So sun doesn't shine for 5 days. If your plant is stressed and doesn't have enough energy in reserve, then it's going to start breaking down proteins to try save at least some seed for the next generation. Okay, so protein breakdown, it gets really hot, or you don't have enough water, and so the plant needs some energy, needs more water, and it starts breaking down those proteins. Proteolysis, or building proteins. I want you to think about your farm, your operation, and think about anything that could potentially slap your plant from actively building proteins to breaking them apart. Breaking them apart. What happens, and I want you to think about every operation that you do. What happens when you cultivate? How does your plant respond? What happens when you put out a pesticide? How does your plant respond? What happens when you put out an herbicide? How do your plants respond? What happens when you put out a PGR? How do your plants respond? Do you like what you see? Or are our actions causing the proteins to be broken down for 2 days, 3 days, 5 days until the plant is able to recuperate and start building proteins again? And here is another image of just, this is what insects can digest. Broken amino acids, broken proteins, incomplete nitrogen, just chaos. That's what brings in the thrips. What causes that? What's the reason for that? Well, it can be a number of things. You can have excessive applications, which happens often when there's too much nitrogen, too much potassium, and it's it's antagonizing calcium uptake, or it's antagonizing magnesium uptake, or you don't have enough sulfur and molybdenum for the amount of nitrogen that's out there. So you have all these free nitrate molecules, but you don't have enough molybdenum to convert them into complete proteins. And the insects go, food here. So think about insects not as the problem, but as a messenger. Think of diseases not as the problem, but as a messenger that the plant is sick. Now, how many of you, if you had a piece of bread, you forgot about it, laying on the counter there, and you got home and it's moldy? Well, would you spray it with something to kill the mold and eat the bread? No? The messenger, the mold, is just saying this is not fit for human consumption anymore. What if the insects and the diseases that we are challenged with are the messenger? Are we killing the messenger and just ignoring the root cause? And that's why we're here today, is to help you discover what the root cause is. It's different for a lot of people, and yet it's very similar for many of us. Because all of you know machines, you all know how important it is that every part is working. You just think of your cotton pickers. Just think of your tractor. If one piece doesn't work, if one injector isn't working, what happens? You lose power. And you don't just go on and on and on and then another, you fix it. You don't just put on a quieter muffler so you don't hear it. You fix it. And so in the same way, in the plants, within every leaf, within the root, within the soil, within the whole system, there's many, many, many signals that are being sent. There's many reactions that are happening. And the more that we can do to manage those, or to encourage the plant, or to empower the plant that those reactions can happen well, the more likely our plant is going to be able to resist well, or not even be desirable for insects and diseases, because it's now a healthy plant. So, balance is the key. If our photosynthesis goes down, that means there's fewer sugars to the root system. Right? So remember, we're deficient in magnesium, we're deficient in iron. We don't know if we have enough manganese or not. We tested it last year and it showed okay, but maybe our plants are showing a bit. Whatever it may be, if your sugar to the root system goes down, it's kind of like if you didn't feed your crew for 2 weeks. You probably wouldn't have very many employees if you don't pay them, right? And so if the biology, the bacteria, the fungi, all this life in the soil isn't getting energy, isn't getting food, they're going to slow down. Of course, you need to be sure that you've not annihilated all of your biology and that there's even still biology in your soil. And James can attest that earthworms supposedly weren't a part of New Mexico agriculture. Well, earthworms are now a large part of James's farm. It's about life in the soil. So make sure that you have life, and Rochelle is going to follow up with some practical ways of doing that. But continuing through, so we have less active biology, which means that our mineral absorption is going to be slower. So now we don't have all this bacteria and fungi mineralizing the nutrients in the soil, so that means we have less nutrients coming up into the plant. So what does that mean? Now we have less magnesium, we have less iron, we have less nitrogen. Our potassium starts failing, which means we're not able to move the sugars down to the roots. And now we start seeing pests. We start seeing diseases. And now our plant's more stressed, right? You look at those plants that have thrips on them. They're not photosynthesizing as much anymore because their vascular tissue is damaged, and so they're not able to feed the roots as effectively, which means you'll have less biology. And what's the fix? Kill the bugs. No, it's not. And sometimes you need to do this. I want you to understand me correctly. Some of those pesticides are tools that we need when we messed up or when nature threw us a curveball. But to farm with that mentality of, I see something bad, I must kill it, won't get you where you want to go. It won't maximize your success. The opposite is also true. if we increase photosynthesis. So maybe we figure out a way to irrigate more effectively and not have any glitches with water uptake. Maybe we realize by sap analysis or by looking at our plants that we're deficient in manganese, and we address that, and we increase our photosynthesis by 15 or 20 or 30%. What's that do? Does that mean you now have taller cotton? Does that mean you have more cotton bolls? Well, hopefully some of that, but it primarily means that there's more sugars left to go to the roots, and we'll talk about the sugar sinks in just a bit. So when you have more energy to the roots, that means more biology, that means a better microbial system, which means you're going to have more nutrients becoming available to the plant. And so now the plant has more iron, the plant has more magnesium, the plant has more of what it needs to be healthy. And if that happens, now we don't see as many pests. We don't need to put out as many fungicides. Maybe we can even not put out any insecticides at all. Very possible. Because our plants are in protein synthesis. They're building proteins more than they're breaking down proteins. Let's talk about sugar sink management. What do I mean when I say sugar sink? Where can the sugars go? Roots. Where's another place that the plant can put its sugars? Fruit. About the new growth. So we have 3 primary sugar sinks, or places where the plant can deliver sugar to. Let's think about this size plant, this size cotton plant. And now let's think about photosynthesis, let's think about protein synthesis, and let's think about sugar production. What did you in your program in the last season do to enhance photosynthesis? What did you do before these plants were planted to make sure that your plants have all they need for efficient protein synthesis? Is there a good symbiotic relationship with microbes in the soil? Are those roots feeding the biology? Or are they overwhelmed with nitrogen? Is there a possibility that you put on more nitrogen than this size of plant might need? And what happens when you do that? What happens when you take in way more, we could just say water for us, fine. What happens if you drink 5 gallons of water? You know, it creates a problem. Things that are okay in small amounts can be problems when they're overdone, when there's too much. At this point, these plants have 2 sugar sinks, the roots and the new shoot. At this point, the plant has 3 sugar sinks, the root, the new shoot, and the bulbs. The primary sink, the one the plant is most concerned about, is the bulbs, the fruit, the seed, because the plant wants to make sure that it has a viable seed for the next generation. It wants to have seed that have enough energy to grow, which goes to another point that Kip made about poor seedling vigor. And we could talk for a while about that. I don't have it in here, but plays right into this. The bulbs, and then the new growth, and then the roots. What determines where the sugars go? How does the plant decide where the majority of the sugars go? There's a hormone called auxin. Auxin is synthesized in the new growth tip. Auxin is also synthesized or built in the seed. Now, this is where we're going to talk about the shed, the drop. What happens? Why is it happening? And what happens after it happens? If you can connect these dots, I think cotton farming will be all the more exciting. There are many reasons why the shed could happen. It could be related purely to proteolysis and something that happened, a certain operation or something that happened in your farm that caused the plant to go into protein breakdown for too long. And it's not photosynthesizing enough. It's not building enough proteins, and it says, I can't finish all these bowls. These must go. It could also be that there's an imbalance in vegetative and reproductive energy. The cotton plant is very vegetative by nature. And we do very well in helping it along by putting on plenty of nitrogen, especially early. And then sometimes there's nitrogen applications later. What if the nitrogen application is causing the plant to say, "Ooh, so much nitrogen"? And guess what? Nitrogen is synergistic with auxin production, which is going to enhance vegetative growth, which means more of the sugars are going to be translocated to the tip. The plant's going to say, auxins are here, sugars go there. The highest concentration of auxins, so too much nitrate nitrogen can cause that. And a proper balance of that, which I'm going to leave to Rochelle, of the other minerals that are synergistic with cytokinin, which is the hormone that's produced in the root and keeps the root dominant instead of the top growth dominant. Now, let's go and see what happens when we have all these bowls, all these squares. And I think maybe it happens after a rain. It happens when you get a flush of growth. There's a number of reasons why it can happen. But when it happens, then you get a flush of growth and you need to quickly hit it with a PGR, right? The key here is that we retain these bowls, because as soon as these bowls drop, we have more sugar than we know what to do with. And there's only one place to go with it. That's to the new growth and to the roots, if we have enough active root growth. See, something else that happens is in a plant's life, it will go from being root dominant to being vegetative or new growth dominant. And so the hormones balance shifts, and that affects where our sugars go. So if we can keep these bowls, if we have enough enzymatic cofactors for auxin synthesis within the bowls, then the sugars go there. And if we have, remember, this is first priority. So if we can use up most of the sugars to fill the bowls, we don't have to worry as much about this big, tall, leggy cotton, because there's no energy left for that. We're putting it into the bowls. So, these are just some pictures in closing. One interesting one here that we received from Texas, where they had bollworms, and I understand it was pretty well stripped. And the grower was like, well, what can I do? So we put on the Accelerate, which is the reproductive energy product that we use, and put on a fairly heavy rate, and they see cotton boll clusters. I don't know if any of you have ever seen clusters of cotton bolls, but it's amazing. It's amazing to me what plants will do when we give them the chance, when we work with them and not against them. So I will let Rochelle take the next part.
Well, I'm Rochelle Robertson. I've been here with James alongside his journey, and I'm very thankful for that. So hopefully I get to kind of join some of you in your journey as well. I'll apologize. Lo siento, mi español no es muy bien. You know, I learned like 3 words in college, and they were sí, cerveza, and baño. So that's all I have. I'll work on that though. Probably no surprise that the industry has been strongly into nitrogen, phosphorus, and potassium, and David kind of touched on that. And that's not to say that we don't need nitrogen and phosphorus and potassium, but the over-application and the timing of those products is very essential in our growth and how we want to keep things balanced in our plants. If we have plants that are in that vegetative state, so if we have a lot of these products, it's going to put our plants in a very strong vegetative state, and you might drive by these and think, boy, they look really lush and green and healthy, but they are actually very lacking in that reproductive energy. So we're not going to have enough energy for a lot of flowers or a lot of fruit, which is bulbs. which is where your money comes from, right? If you're not familiar with what drives that vegetative energy and what drives that reproductive, the 4 nutrients that will drive your vegetative state will be nitrate nitrogen, potassium, calcium, which we'll talk a little bit about, more so how we use it here at AEA, and chloride. Reproductive nutrients are really everything else, but your key players are going to be phosphorus, manganese, and ammonium, and then a balance of everything else. A lot of these are still essential. So our focus at AEA is to have very strong vegetative plants, but we also want to create that reproductive dominance and then also have that balance of having the vegetative state. So what does that mean for us? That means that you're going to have really strong growth, so you can have new shoots growing at the same time you're having very tight internode spacing. And so I'll give an example of that. We can have 2 weeks worth of growth and it's 12 inches. And we can have our internode spacing at 6 inches. Or we can create a plant that is having that same amount of growth, 12 inches, 2 weeks, and we can have internode spacing at 2 inches. What's going to make you more money? So that's our goal here at AEA, is to keep that energy and have that tight internode spacing, have that reproductive dominance. I want to kind of back up just one step and just kind of clarify, because your plants are always going to be kind of going back and forth between these 2 states. They're always going to be in a state of reproductive and vegetative, and we can manipulate that really easily even with just one foliar application. So again, our tight internodes mean more blossoms, right? More bolls, more yield, more money. This balance is also going to lead to healthier plants. So if we have healthier plants and we have less boll drop and that higher quality lint, we're also going to have fewer applications needed of any of your sides. So pesticides, herbicides, fungicides, some of those we can actually get rid of altogether. So our AEA product focus, again, is going to be on those reproductive nutrients, but our vegetative is going to be on calcium. And this is very important. So calcium is a little different, or very different, than getting our growth from nitrate nitrogen and these other sources, because calcium is going to give us that tight internode spacing. It's going to actually give us that growth without getting really leggy, which is what we want. If you were to dive into James's program, which this is actually a piece of that, there's many other foliar applications, but these are just 2 of those. You'll see a common theme of products that we use over and over. 2 of the main ones are going to be Accelerate, that reproductive nutrient balance of manganese and phosphorus, and then also our holocal. We also drive protein synthesis with our photomag ingredients, so David touched on that importance of having really high photosynthetic nutrients, and then also balancing our micronutrients. Holocal is going to be a blend of holocal calcium and then also a little bit of boron in there as well. So that's going to drive our vegetative, really tight internode spacing with that calcium, and then again, Accelerate's going to focus more on the manganese and phosphorus aspect, but also has some other blends here at AEA that are going to drive a natural reproductive energy. It also promotes really, really awesome flowering at the same time as fruit set. So David shared a few pictures of that earlier. Photomag as needed, and then also the balanced micronutrients, and we're going to get that information like, okay, how much of these are we going to add, and which micronutrients will be based off of plant sap analysis, so we don't guess at what we're going to be applying, right?
So now you've heard a little bit about the science, you've heard a little bit about the product. Now I'm going to talk to a little bit about the reality. My family started growing cotton in the 1950s, In 1971, we built a cotton gin. Our cotton gin actually now is in Asunción. It's part of IASA. The way that we've always grown cotton is a bit like driving a car with one foot on the brakes and one on the gas. We tend to apply a lot of nitrogen, and then we have to slow it down with a lot of growth regulator. How many of you apply pre-plant nitrogen? How many of you apply the equivalent of 50 pounds of pre-plant nitrogen per acre, which would be like 150 pounds per hectare? This is the historic way that cotton is grown, and as Javier tells me, this is the way that it's grown in Mexico. But as they were talking about, when the plants are fairly small, there's no way for that plant to deal with that much nitrogen or the carbon dioxide that's released from that much nitrogen in the soil at that time. So a lot of times, you know, we talk about light, we talk about water. We've been told all of our lives that we're dealing with a law of minimums in production. But one of the ones that we don't talk about is the law of minimum obtaining the carbon dioxide coming out of the soil. And one of the worst things that we can do is over-apply nitrogen early, because we flush all of that carbon dioxide out early and we don't have any when we need the crop. I take a lot of pictures, and I send a lot of pictures to David, so most all of these pictures are, well, I think all of them are of my crop. We don't guess any longer what the crop needs. The only thing that we do without a test is the application of a soil primer before or during planting. So this cotton right here has nothing applied to it except for a soil primer to nurture that along. I think we put a little bit of zinc with this and maybe some iron, but that's all. No nitrogen, no phosphorus. This is actually the first place that we take a sap analysis test. So anybody in here know what a sap analysis test consists of? I know, Colton, you guys ran some this year. So a sap analysis looks at things a little bit differently. Historically, in agriculture, we've looked at a plant tissue analysis. And the best way that I can explain the difference between a plant tissue analysis and a sap test is this. It would be like going to your doctor and your doctor saying, "Dosey, I'm going to need your left arm." And he's going to cut that left arm off, and he's going to put it into a fire, and he's going to burn it, and he's going to take everything, and he's going to analyze the ash. That's how a typical tissue analysis works. So they analyze the ash after they've burned the tissue. Really, all you needed was a blood test. And unfortunately, because they've taken the arm, they've also taken your fingernails, the bone, the hair, all of these things, and really all you were looking for was the analysis of what was in your blood. Advance in Eco-Agriculture works with a company currently out of the Netherlands that developed a sap analysis. When did you guys start using it? 2011? 2013. So this is, it doesn't seem like new technology. It's 9-year-old, but it's new technology as far as agriculture goes. We take, on a plant this size, all we can get is what we consider to be an old leaf. And at this point, we start testing the analysis of that plant. And that plant's going to start telling us immediately, on just one leaf sample, we can start seeing, because we have enough data points to understand what that plant wants. At that point, we applied our first foliar application. At this growth rate, really all we were looking at doing was keeping the plant healthy, keeping it balanced, keeping its sugars to keep the bugs from attacking it. Heavy to calcium, low on nitrogen. We actually did apply a little bit of nitrogen here. How many of you in here know Javier? Javier told me, we got to put nitrogen on this crop. We got to put nitrogen on this crop. ¿Verdad, Javier? Recuerda. Because that's what we do. We put nitrogen on there. At that rate, we put nitrogen on there. So we made a deal. Said, okay, Javier, we're not going to put 30 units of nitrogen out. We're going to put 10 units of nitrogen out. And then we're going to take a test. So we put the 30 units of nitrogen out in the drip. We took a test about 2 weeks later, and all that the test told us was we really didn't need the nitrogen. So we had to make, because Javier was new here, and I was new with Javier, we had to make some concessions so that we could all be happy going along. I didn't want him to think that we didn't value his input, but I also wanted him to understand that what we were going to see was that a lot of our old perceptions needed to be changed. I'm going to scroll through a lot of these. This was about, we really started squaring at this point. We started kind of flipping through some of our foliar program, really starting to improve. If you can see on this side, I know it's kind of hard to see, but we've got a lot of squares. Starting to get a lot of blooms. Back again, kind of to that smaller, maybe some of the first flowers. I do like taking pictures. I really love the beauty of Pima Cotton in the spring. To ask all of you guys that are cotton growers here, if you were to guess at that, how much nitrogen applied, how much applied nitrogen in the form of any type of chemical was put on this. If this was on your farm, how much would it be? ¿Cuántos te cree? Ustedes que llegan temprano, tú sabes. Pero para los que llegan, es la primera vez que llegan aquí. For everybody that this is your first time here, how much would you say that I had applied there? How much? So Dr. Jinfa Zhang thinks that I've put out 20 units. 10. And only because only because, and it's not to say that nitrogen is not important. I think we have to clarify that. We have to make sure that we know what nitrogen needs. Nitrogen is an important element. Nitrogen is an important fertilizer. But it is not number one, as we have been told our entire careers. At this point, Doctor, you're correct. I've finally gotten to that 20 unit. Actually, this is 22 units. So 20 pounds, 20 libras de urea por acre. Es todo que apliques aquí. 50 libras por hectare. In ese momento, in this time, how many of you applied? 300 kilos por hectare. ¿Y cuántos aplicas yo? 50. 50 kilos to 300 kilos. How much money is that? I bought it at 800. I got a better guy. $800 per ton nitrogen. Our cost is $1.05 US money per unit. $1.05 per unit. This program, everyone likes to talk or everyone likes to worry and everyone wants to say, how much does this program cost? When we open this up to question and answer, I know that's going to be one of the questions because it's the first thing that I've asked. My total applications for this crop is $400 per acre. Now, let's think about what we've applied and what we have not applied. How many applications of growth regulator did you apply?
Maybe 3, 4.
¿Y cuántos litros por aplicación de PICS aplicas ustedes?
En las 4 o 5 aplicaciones hasta 1,5 litros. En 3 o 4 o 5 aplicaciones, 1,5 litros. High concentration.
I'm going to ask that in English as also. So they're at about 1.5 liters per hectare of PICS. Keith, where are you guys at? They got 5 applications of PICS on. 18, 24, and 32 ounces. So you're at 1/2 gallon. They're at 1.5 liters. Bronson?
That's my agronomist.
¿Quién sabes? Más o menos. Anybody want to guess how much I have on this? 0. My old way of managing growth, David talked about it because he knows that's the way I used to manage growth. My old way of managing growth was through management of water. I don't stress cotton anymore. Not one bit. It was one of the scariest things that we ever did. We irrigate cotton now on a continuous basis to the point that we're almost saturated. We still want to have good air exchange, but we have plenty of water out there. I'm using less water now at the end of the crop because we're actually storing water early. One of the problems that we always had was when we managed our growth by managing irrigation, we kept things so dry that when the plant did need water, we couldn't get enough out there fast enough. Now I maintain, and I have the tank full all of the time. How many of you fought bollworm this year? Most of you have boll guard technology. Pima Cotton has no boll guard technology. In dimming, everyone sprayed for bollworms 2 to 3 times. Maybe some of them got a little too anxious. I kept telling them, relax. We haven't sprayed for bollworm here in 3 years. Chinche, stink bugs. How many of you had stink bugs? ¿Cuántos?
5 aplicaciones.
5 applications. No aplicas nada de insecticida, nada de fungicida, nada de growth regulator de PICS aquí en 3 años. I have not applied one single fungicide, insecticide, or growth regulator for 3 entire crop seasons. The hardest thing sometimes to change is that which is between our ears. Even weeds now, we look at weeds on our farm differently. I used to think that weeds were here because they saw an opportunity. Weed seeds were only opportunists. Now we look at weeds as an indicator of a greater problem, of a greater imbalance, of a greater loss of bacteria and fungi in our soils, and that the weeds are actually there in some ways to assist and to help us in our transition. So this year is year 2, the second year of organic production, successful organic production for us. So in 2021, we had organic Pima Cotton and organic paprika peppers. This year, 2022, we have organic Pima Cotton and we had organic onions. The system works. Nature is a whole lot smarter than we are. And the system functions a lot of times if we can get away from it. What is your worst weed on your farm right now? You said it. Quelite, pigweed. Everybody in the Southwest knows this. It doesn't matter. We can say it in English. You know, you say it in English and you got to spit. You say it in Spanish, quelite, you got to spit. Who's been farming longer than Roundup? Keith. I gotta ask, yeah, Keith, my dad. I gotta ask, how bad was, I'm sorry, pigweed in 1993? Not a problem. Dad'll say not a problem. En el año 93, ¿cómo está el quelite ahí en su campo? No era problema. How did we go in 29 years from it being not that bad to we can't control any of it anymore? What if the weed is an indicator of a greater problem? What if the weed has adapted to show us, what if the weed is actually adapted to try and fix something that we've been changing in the soil structure or in the soil biology? This is when trust me, 4 years ago, I would have told you were nuts for thinking that. But today, whenever I look at my own farm, I didn't have a problem with pigweed 4 years ago because Roundup killed it. It was somebody else's problem. I remember sitting in meetings and everybody saying, it's coming, it's coming. Nah, nah, it works. Doesn't work anymore. At some point, we're going to have to change this. The $400 that I applied was all nutrition and all applications, not inclusive of herbicide and seed. We spend about $10 per acre inch. So acre inch of water cost us about $10. The whole crop, we've got about 32 to 33 inches applied. It's going to be about $320 for water. So the first one that we did not apply, one of the first and foremost things that they told me to stop doing was applying phosphate fertilizer. The founder of Advanced in Eco Agriculture's name is John Kemp. I went to a school where he talked about growing cotton. He asked the majority of the group, so this was in Lubbock, how many of you apply phosphate fertilizer? Whenever they asked the guys in Lubbock, they said, how much are you applying? The majority of the room, and for easy math, let's say everybody here applies 200 pounds of 1152. So the next thing that John asked was, out of 1152, 11% nitrogen, 52% phosphorus, how much actual phosphorus are you applying to your soil? And so everybody sat there and they're like, well, duh, 52%. You know, 104 pounds. So John kind of sits and he goes through and he starts asking everybody, if we understand the way that phosphate fertilizer is made. So when you go and you take rock phosphate mined, they put it through a process where they split it. So rock phosphate comes out of the soil, tricalcium phosphate. They take it through a process where they split that with sulfuric acid. They bring off the phosphate, they make it into a nice little prill, and they sell it to you. And they take those calcium and they throw them out the door. So the very first lie that we've been taught is that we're applying this available phosphorus out there. When in reality, the very first thing that happens when we put phosphate fertilizer out is it goes and it finds 3 parts of calcium and it attaches back to it. So now we've tied up 3 parts of our calcium in our soil. The other thing is, and John is truly brilliant, and that day spoke to me on a level that was beyond anything that I could have ever imagined. But by the time it was all said and done, and he taught us that most of that phosphorus that we think that we're buying is in an oxide format and not plant available at all, where we thought we were getting 104 pounds of available phosphorus, when in reality we were getting it down to 6 pounds of available phosphorus. Has anybody bought phosphate fertilizer in the last few months? Most of us don't. Does anybody have any idea where the phosphate price is right now? Over $1,000, $1,100. So when we talk about the first savings that we did, if I was applying 200 pounds, I've already saved myself $110 by not putting out 200 pounds of phosphate. We didn't always apply nitrogen, but a lot of the guys in the room are applying. So let's say we just put out 100 pounds of pre-plant urea, which is kind of this, I think, was the industry standard here. But if you're putting out that at a minimum, even if it's $800 per ton, I'm not putting that out anymore. How many times did we go across this whole crop? 5 times. I put 5 foliar applications on this entire crop. You put that out just fighting stink bugs, chinches. The second one is, and we are still working on yield data, we got to stop talking about production. Who makes the biggest yield doesn't always make the most money. Who makes the most money makes the most money. And one of our problems in agriculture is we all want to talk about, oh, I made six bales. Oh, I made 7 bales. I don't really care what you made. I want to know how much money I made. Because money pays the bills. More questions? Brian, thank you. How many SAP tests we do per year? I think I should do more, but I think as we start learning more, we want to start learning more. We do it at all critical control points. So when we have a true leaf, we take a sample. At first square, we take a sample. At first bloom, we take a sample. At anything that makes a change in that crop, we start making a sample. We know more about growing cotton today, well, we think we do, than we did 3 years ago. And the reason that we know more about it is at least we can make a plan now based on 3 years of sampling on our farm. The reason that I say I don't sample enough, I saw some SAP analysis from some growers in Mississippi that are sampling every 2 weeks. They're young, they're ambitious, they've got some young people working on the farm, and they're SAP sampling more often. We took it as, if we haven't done anything to the crop to make a change, what good does it do to take a sample? But when I start looking at some of their data, I'm like, even though you didn't apply, you can clearly start seeing where the plant starts changing as things go. So we may continue on a broad scale sampling as we are. We may take a few fields and sample more rapidly.
That's not to say that you can't learn something, though, at like kind of what James was talking about, at those critical points of influence. It kind of depends on how much data you want what you want to look at, and that's kind of like we really basically make a program or things on what you're capable of doing on your farm.
And we really started with this just, you know, David tends to get very scientific, and 3 years ago that made no sense to me. It was here, and I was here. But now that I've started learning how all of these things connect, now I'm somewhere in the middle where it kind of makes sense, and like I see the importance of it.
Have you seen a difference in like water consumption? You think if you would have pulled more samples after the rainy thing started late July, late June?
This was a strange year for all of us. How many of you how many cotton crops got away? Like, how many of you have cotton that's this tall now? We all got nervous when the weather changed, when the climate changed, whenever we started getting cool. Let's go back to the 3rd week of June. What is our temperature supposed to be here? Our normal temperature in June should be 100. We were 85. I actually got nervous. There's correspondence between David and I, because I said, I don't know what's going to happen. I've never seen this before. This isn't a good place to be. It's 85. We're high humidity. The monsoon has already started. This cotton's going to go vegetative like crazy. Because that's what we've been conditioned is going to happen. We've got sap data all the way through, all of that time. And every one of them is going to have a date on it, but nothing got crazy because we just continued to sap. We just continued to test. We applied what we needed to apply. And the biggest thing that I can say is we don't guess, we test. And as inputs continue to rise, as nitrogen, as phosphorus, as everything else continues to rise, we have to completely get rid of this guessing. It's too expensive to guess anymore. David asked how many bowls we lost, how much percentage of our crop we lost to the ground. 0. I have 600 acres that I finished the year from July till now on less than 500 gallons. And Pima, so our county average, the municipal average, if you will, here is 880 pounds per acre. And we just got the yield data back, and it's still better than that, even being finished on 500 gallons. So there's some resiliency built into the system that I didn't have before. We lost some crop, but I'm ecstatic to say that we made as much as we did after losing that much water. How many apply nitrate fertilizer? You want to use water, apply nitrate. So if we look at the scale of nitrogen, nitrate is at the bottom, ammonium, urea, and amino protein nitrogen is at the top. Each of those has to go through a series in a process. If you apply nitrate, it has to convert to ammonium. Ammonium has to convert to urea. Urea has to convert to amino acid, amino proteins. Each one of those processes uses energy. And every time we use energy, we lose water. So can you go back to that? So our goal is different. It's very different. Why is there still so much in cotton growing? I know there are studies out there being funded right now about testing nitrate levels in cotton, and people are still being told that nitrate levels, maintaining adequate nitrate levels, is an indicator of overall fertility. Why is that still the case? But when you look, nitrate is still important. nitrate is important to me. I want to put my nitrates, if I can farm with nitrates at 0 and my ammonium levels being low, so the ammoniums here are fairly high, but if I can keep these nitrates at 0 and my ammonium's in the optimum level, ammonium is 90% of why we have chewing and sucking bugs. So the higher ammonium is like a neon sign out there telling all the bugs, eat me, eat me, eat me. So the more that we can stay away from ammonium and the more that we can stay away from nitrates, the better off we are and the less problems that we're going to have stress-wise in the plant as well as bugs. Profound thing happened to me a long time ago. I guess it was in 2018. This was the first indicator. How many people grow peppers? Come about August 5, August 10. What does everybody in the pepper industry start fighting? Mildew. Powdery mildew. I was taught that powdery mildew, we had to start spraying fungicides. Boy, you better start spraying fungicides about the 15th of July or that mildew is going to get away from you. Well, the funny thing about it is, I was the cooperating operator for Yara for several years on a test, on a trial for CAN 17 or calcium nitrate fertilizer on peppers, and how CAN 17 would elevate and you'd get more yield per acre if you used CAN 17. Yara used to give me fertilizer to prove this, but nobody ever told me that the majority of my problems with powdery mildew went back to that. Now, how many of you, is this the first time you've ever heard that nitrate spurs mildew? And it's a response. It's because that plant is so unhealthy that it can't fight it off itself and the mildew sets in. That mildew is not there in competition with us. It's there because we've made a mistake.
With Phytophthora is a very different organism than the mildew, and the level of carbon in the soil has significant impacts on the Phytophthora also.
My brother operates our pecan orchards. We pretty well test the pecans the same way that we test cotton. We tested peppers the same way we tested the pecan crop or the cotton crop. The difference is now peppers and cotton are a little bit different than pecans. Pecans, David will say, pecans, fruit, like apples, cherries, pecans, even grapes to some extent are simpler because you have one, if everything works right and we don't have a freeze, we have one flower set, we have a pollination period. After we have a pollination period, you've got cell division, and in that time of cell division, the most important thing is cell wall structure and cell wall strength. And then you go from cell division to cell growth. With peppers and with cotton, we have to maintain those a little bit differently because we are still trying to grow vegetation while still putting on healthy and good cell division as well as cell growth. With a pecan crop or with a cherry crop or a peach crop or an apple crop, the products are similar, but the timing is going to be different because you're going to laser focus on certain nutrition at certain times more so than we do with cotton and peppers. Cotton and peppers, we really want to maintain it as balanced as we can throughout the entire growing season.
You can think of the vegetative reproductive energy. If you think it as a balance, so you want it for peppers and cotton and beans, you want to be a little bit vegetative and then reproductive, and you just give the plant what it needs, it will figure that out by itself. If we're not putting on excessive nitrate and slamming that all the way to vegetative or depriving it of water and making it very reproductive. So with pecans or a single fruiting crop where we have all the flowers at once and all the cell division at once, we can be very heavy with an application. We can really support the reproductive energy, really support pollen production, really support pollination, and then really focus on cell expansion and filling that fruit. So it's the other thing that is easier with perennial crops is you're not establishing the plant every year. You're not tilling the soil. You're not your biology has better opportunity to establish.
We struggled, I'm not going to lie. So I have a little bit of a different problem than most people do. Does anybody here struggle with salinity or sodium? So do I. So we used to be able to, my father was a wonderful farmer. When he started growing paprika, we used to could make 5,000 pound paprika. 3 years ago, we made 2,100 pound paprika. We have a real problem right now in the pepper industry. I thought that we would be able to flip a switch here and fix things. It's not that simple. We've got years. Cotton was easy. Like for me, our increase in our cotton yields and our decrease in our was super easy. Like it was flip a switch and we're going to grow better cotton, but we're going to spend less money. It's been more difficult in our onion crop, and it's been more difficult in our pepper crop. And the two of those I put back to I have high sodiums in my soil, along with a lot of disease. And then the third one is, especially in the paprika, and everyone in here that grows paprika is probably going to nod their head when I say this. We have absolutely terrible seed quality.
Genetics, right, because when you consider a plant that's compromised, when it's filling those seeds and your sugar synthesis, your photosynthesis is down, your protein synthesis is down, you have phytophthora in the seed. And I've been asking James, well, how many acres would it take for you to produce your own onion seed? We, like so many other things, have been led to believe that it's some difficult thing to grow your own seed, and it's not. And there's things about local regions and seed production that we could talk about. But then there's also the quality. If you have, let's say that on 5 acres or on 2 acres, you could produce all of the onion seed that you needed to plant your whole farm. Well, on 2 acres, you would be able to put a foliar application on every week. You'd be able to make sure they have optimum fertility. You'd be able to make sure there's lots of carbon. You'd be able to make sure that all the processes we talked about are functioning at maximum capacity. And when you put that seed in the soil, not only is it conditioned for your environment, for your soil, etc., but it has a lot more energy packed into it. Now here's just a little bit of an interesting thought. James mentioned, pigweed. And when did we start having this problem? Consider with me that glyphosate, the active ingredient of Roundup, was first patented as a chelation agent, meaning to tie up or to hold. And that's a very, very strong chelator. I like to use the analogy to help us understand the strength of it. If you take your vitamins in the morning, do you prefer to have your vitamins in a capsule that's made of some gelatin or wood or plastic or stainless steel? That's chelation, okay? Something that a plant isn't able to absorb, the chelation is to cover it so that it can be absorbed. If you took your vitamins in a stainless steel capsule, it would probably create a lot of problems. You wouldn't get very much out of what you're taking. Consider that glyphosate is a very strong chelator of the metals, especially manganese and iron and calcium. And so think with me how many molecules of glyphosate, how many chelation sites have been put in your soil. And now consider with me also a professor in Cornell University stating that if you don't have sufficient levels of manganese in your seed, they will not germinate. And now we think about seed vigor, and we think about, well, even in some crops, glyphosate is used to terminate the crop so that all of it's at the same stage. And now we wonder why we have seedling vigor. I believe we have major problems with manganese availability. And I think it leads to seedling vigor, and that seedling vigor, the whole genetic potential is determined when that seed is growing. And so, yes, you can select from, the characteristics you're looking for. That'll make a big difference. But the amount of energy that's within that seed is going to determine how quickly it comes out of the soil, how quickly the roots go out, and that's going to determine the whole yield. It's determined within days after you plant what you're going to yield. That potential has been set. And now it's only downhill from there. An example of that, because this is again a psychological thing, a way of thinking. We think we put on fertilizer to increase yield. I put on fertilizer, I got a higher yield. We don't increase our yield. The genetic potential of the cotton is highest when you put it out there. What's the highest cotton yield you have ever heard of? So let's say that 14 per hectare is what you're harvesting. Then probably the genetic potential is 18 or 20 or 25. And that genetic potential, we put the seed in the ground, and we're going to lose some of the potential that's there because there's going to be stress. But that's our goal, is not to increase yield, but to reduce stress so that we don't lose yield. Think of the yield at the highest point when you plant the seed. And everything you do to stress that plant is going to reduce the yield potential, and finally you harvest 14 bales. So that's a good yield, but we already lost a lot. What if we could lose less? When you think about yield in that way, it's like, it's not just about putting on fertilizer to increase yield, it's about reducing stress and giving the plant what it needs to keep that yield from being lost.